Good morning to all of you. In previous session, we have seen natural response and free response, as well as forced response. The natural response or free response is also done as the transient response, right? And how that forced response can be termed as the steady state response when you are applying sinusoidal function as an input and the system is producing sinusoidal output. So in that case, that forced response will be termed as the steady state response. We also solved one example where we identified these transient response and the steady state response. Right? In today's session, we will be discussing causality and stability of Lti system in Z domain. Okay. We already discussed the causality and stability of Lti systems in time domain in terms of the impulse response h of n, right? So the causal Lti system is one whose unit sample response h of n satisfies the condition, that is h of n should be equals to 0 for negative values of n. Okay, we have derived this expression when we have seen or discussed the causality of Lti system in the time domain. Okay. So the causal Lti system is one whose unit impulse response or sample response h of n satisfies the condition h of n is equals to 0 for negative values of n, right? So when you are talking about causal Lti system, obviously it will be processing causal signal. So the ROC of the Z transform of system function or the causal signal, the ROC of the Z transform of a causal sequence or the system function of causal system is the exterior of a circle, right? So here we are defining the causality of Lti system in Z domain by using its region of conversion, that is ROC. Okay, so we can state that Lti system is causal if and only if ROC of the system function is the exterior of a circle, right? So Lti system is causal if and only if ROC of the system function is the exterior of a circle. Okay, basically this circle should have radius, you can say r should be a finite. Okay, so whatever circle you are plotting for ROC, right, that circle should have radius less than infinity. That means it should be a finite radius circle, right? So the ROC of Z transform of a causal sequence, or you can say that system function of its causal system function, okay, is exterior of a circle. Okay, so Lti system is causal if and only if the ROC of the function system function is exterior of circle, right? So that is the condition for causality of system in Z domain. Similarly, we can define the stability. We have already seen the stability in time domain where we define the stability of LTI system in terms of the impulse response. Correct. So here also in Z domain, the stability of a LTI system can be defined in terms of uh, your system function, that is h of z, right? That is h of z is nothing but the z transform of function h of n. Okay, that is impulse response, small h of n, right? So the stability of LTI system can also be expressed in terms of the characteristics of the system function. Characteristics of the system function. When you are talking about system function, so system function is nothing but capital H of z, right? And this H of z is nothing but H of z is the z transform of impulse response H of n. Okay, so this is the formula for z transform. Okay, signal multiplied by z to the power minus n, n is varying from minus infinity to infinity, right? So here in case of z domain, the stability of LTI system can be expressed in terms of the system function, that is h of z. As we have seen already, a necessary and sufficient condition for a LTI system to be bounded input, bounded output stable is this h of n should be, that is impulse response should be absolutely summable, or it should be finite, right? So it should be not equals to, it should be less than infinity. Okay, so it should be absolutely summable, correct? This thing we already discussed, okay, when we discussed the stability of LTI system in terms of impulse response. So it is necessary and sufficient, necessary and sufficient condition for a LTI system to be bounded input, bounded output stable, correct? So this condition we have already seen, correct? Because we came to this condition when we are considered we are applying the bounded input to the given system, that is x of n is having finite number x of n having finite number of samples, right? So in that case, if your impulse response is also finite sequence, then your system will be obviously a stable system, right? So this condition can be applied to the system function h of z, right? So here this h of z is equals to summation n minus infinity to infinity h of n is there, right? So if you are using this condition, implies that h of z must contain the unit circle within its ROC. So how it will be possible? So as h of z is equals to what? Summation n is equals to minus infinity to infinity h of n into z to the power minus n, correct? So it follows that the h of z, the length of h of z, that is total number of samples in h of z, should be less than or equals to this n is equals to minus infinity to infinity, the total number of sample or this sequence, right, z to the power minus n. So this can also be expressed as this particular term can be equals to what? Summation n is equals to minus infinity to infinity length of h of n multiplied by length of z to the power minus n, right? So h of z will have a number of samples less than or equals to this particular summation, right? So when it will be evaluated on the unit circle, what does it means? So when this expression what were written above, what we have, this last expression I will write here. So it is this h of z, right? Length of h of z is less than equals to summation n is equals to minus infinity to infinity length of h of n z to the power minus n. Okay, so when it is evaluated on unit circle, that means the unit circle, that is for mod z is equals to 1, right? So what we'll get, so if you are substituting z is equals to 1 here, so it will be 1 simply, right? So this h of z will be simply less than or equals to summation n is equals to minus infinity to infinity h of n. Okay, so when talking about the stability of LTI system in Z domain or in terms of its system function, if the system is bounded input, bounded output stable, the unit circle is contained in the ROC of h of z, because as we have seen this h of n should be finite sequence. Okay, so if it is a finite for a stable system, then its system function will be finite. If it is a finite sequence, then this system function will also a finite sequence, right? Correct. So uh, when it will be finite, when we are evaluating the given system function on the unit circle. Okay, on the unit circle. So for stable system, the unit circle is contained in the ROC of that system function or system, right? So hence if the system is bounded input, bounded output stable, the unit circle is contained in the ROC of h of z, right? So again we can state here that a LTI system is bounded input, bounded output stable if and only if the ROC of the system function includes the unit circle. Okay, so that is how we are defining the causality and stability of LTI system in Z domain. Here also we are defining the condition for stability of LTI system. LTI system is bounded input, bounded output stable if and only if the ROC of the system function, again h of z, capital H of z, includes the unit circle. Okay, so why it should include the unit circle? Because this term should be finite. It cannot be infinite values or powers of z there. Okay, it should be evaluated for some value z is equals to 1, right? So here we have defined the causality, right? So LTI system is causal if and only if the ROC of the system function, again it is defined by using the system function, that is capital H of z, is the exterior of a circle, right? So then you can say that the given system is causal. And what about stability? If the ROC of the system function includes the unit circle, then you can say that the given LTI system is bounded input, bounded output, stable, right? So that is all about what causality and stability of LTI system in Z domain, right? Again, these causality and stability conditions are used to analyze or identify the response of system in Z domain. Okay, in previous session we were discussing analysis of LTI system, linear time invariant system in the Z domain. So in Z domain, the causality and stability are analyzed by using the system function, that is h of z of LTI system. Right? So in next session we'll be discussing one example where, depending on the stability and causality of system, we can identify the impulse response of the system using the system function. Thank you for joining this session.